Okay, this video is to look at how to draw a balanced reaction for producing biodiesel. So to make biodiesel you need an oil. So oils are triglycerides, and the classic biodiesel is from the oil that comes from palm trees, so palm oil. In order to make the biodiesel, you need to break up triglycerides. So we're going to react it with methanol, alcohol, and you produce glycerol, which has a hydroxyl group on it like alcohol. That's why it's got the O, the ol sound, and your biodiesel. So a biodiesel molecule is an ester molecule. So if you don't know what esters are, you need to watch the other video. Alright, so tri means three. So to remind you that a triglyceride, palm oil, we're going to look at this at the end of the year, fats. If I wave my fingers at you like this, 3 fingers, it's reminding you that a triglyceride molecule has the 3 parts hanging off it, and you can use your knuckles to look indicate the carbons. So it's a molecule that has a 3 carbon backbone, and it's an ester bond holding the long chain of carbons, which could be, if you took this totally off and put a hydrogen on the end, they would be fatty acids. Okay, so carboxylic acids, but very long, so we're going to look at later on at the end of the year. If they're long, we call them fatty acids rather than just carboxylic acids. Alright, so this bond here is where we're going to break our fatty acid chain off from the glycerol backbone. So the reason that we have to break this up before we can use it as a fuel is because you can't burn this triglyceride, because the oxygen can't attack here to make carbon dioxide and water. It's like trying to burn wax. You can't burn wax as it is. You have to use a wick and get the wax molecules up into the air as a gas. So this palm oil is similar. It's the molecules, the oxygen can't attack it. So we have to break it off so that we get single chains, and then the oxygen can combust, can react with it. So in order to get these 3 chains off, we're going to have to add 3 methanol molecules. So I'll just write the overall. This part here is the part that is going to be, the 2 sections will break up, and this section is going to go onto here, and this section is going to go onto there. Alright, so we need 3 of these, one of these for each fatty acid chain, and then we're going to break it up and make a glycerol molecule. So if we have a look, glycerol is the 3 carbon backbone, and instead of being bonded here, it's going to be bonded to the OH from the methanol, which also makes it an alcohol, hence the name glycerol. Okay, so then this CH3 group gets put on the end here. If you're I'll do it with red. So the carbon is attached to this oxygen. So the carbon is attached to the oxygen, and we would draw the hydrogens coming back this way. If you would do a semi-structural, it would have to be H3C to show that the carbon is attached to. So this is an ester group, and if you have watched the video for making esters, you realise that the alcohol is called, instead of methanol, it becomes methyl. And if this was a 2-carbon molecule, if your carboxylic acid was a 2-carbon one, you would call it methyl ethanoate. But this is so long that they kind of just give up. They don't name this. It's just methyl ester. Okay, so each one of these comes off, so you end up making 3 methyl esters. So you need to be able to balance this reaction. There's 1 glycerol, 3 methanols that you need, and 1 triglyceride. Okay, a little bit more about this. Your fatty acid chain, sometimes people don't realise how long this is. So it's got 14, 5, 6, 7, 8, 9, 10, what I've counted wrong, 11, 12, 13, 14, I think that's right, plus this one on the end. And if you had to count them, there's 14, 15, 16 carbons. Don't forget this carbon. Okay, so it's really long with a hydrogen off every one. So it's a hydrocarbon chain. Hydrocarbon molecules are non-polar, so it's a non-polar molecule. This tiny end up here is polar, but if it's got the hydrogen on the end, so if it's a fatty acid, carboxylic acid, that's really long, this end would be the polar end. So the longer the hydrocarbon chain, the less effect this has at making it soluble. So this would not be soluble, it's too long. So your methyl ester, your biodiesel, this is the whole point. I knew I missed something. Biodiesel, that's what this is. Your biodiesel molecules are non-polar, so they're not soluble. However, this end here can attract water molecules. So water molecules will sit next to it, so it can absorb water. So it will form hydrogen bonds or dipole-dipole bonds with this end. Water will sit next to it, but water will not be around it, so it can't dissolve in the water. It will just attract water molecules, so it's hygroscopic. It attracts water molecules and kind of gets a bit wet. What else have I forgotten? This is soluble because it's got 3 hydroxyl groups on it, so it will bond with water. Methanol is soluble, and the triglyceride oil is not soluble, obviously. So when we look at the next video, we can see that the oil that you start with, it won't dissolve in water, and the biodiesel that you make won't dissolve in water either. In order for this reaction to be sped up, we need a catalyst. And you might remember last year when we form esters, so if this was a carboxylic acid, a carboxyl group, and we were reacting it with an alcohol to make an ester bond, you would have to have acid, sulfuric acid, as your catalyst. So seeing as we're going this way, the catalyst is a base, potassium hydroxide, which is also soluble. Hopefully that is it. Yeah.